Okay. Okay. Can you guys hear me? Okay, good. Couple of updates. Can you hear me? Okay. Couple of updates. Your homework is out, so you have 2 weeks basically. And then the second homework is going to be out again 2 weeks from now. When you've handed in your first homework, you're going to get the second homework. Just see if it's, yeah. Okay. One other update, one of the TAs just informed me that we have about 11 projects from last year. These are kind of like, just randomly selected projects, the kind of projects that students did last year. They've been posted on Piazza, so you're more than welcome to take a look and basically see what the projects looked like last time. I don't think these are like good projects. I think these are pretty reasonable projects, right? Just for you to get some inspiration of what was done before. Okay. TAs, I think office hours for TAs responsible for the first homework is again announced on Piazza. So make sure you know when the office hours are. One advice is that if you wait up until the Sunday or the Saturday before the assignments are due on Monday, you will not get TA's time, right? So make sure that if you have any questions, you talk to TAs beforehand. Okay? Any questions, logistical questions before we start? Good. Okay. So in the next couple of lectures, we're going to look at deep learning and the basics of deep learning. I think that I wanted to introduce those couple lectures. For those of you who've taken the deep learning class before, some of it is going to be repetition. But for those of you who haven't taken this class, we need to cover it because you're going to be using these kinds of models throughout the course and maybe in your final project as well. So, okay. And I also recommend everyone to look at this particular class on neural networks. This is developed by Hugo Larochelle. He's at Google Brain now. And he's put a lot of efforts in like designing and making it on YouTube. And it's excellent set of different topics if you're interested in just ranging from neural nets, sparse coding, to RBMs, to language modeling and such. It's a very good introductory materials over there. Okay, so let me just backtrack a little bit. So last class, we've looked at a large-scale reinforcement learning, right? And we basically said, well, whenever we're dealing with these large state spaces, how can we scale up the model-free methods to prediction and for control, right? And we've looked at basically value function approximations, right? We've basically said, well, one solution to for large MDPs is to basically use function approximation, right? We're going to be replacing our value function parameterized by some policy pi via some parametric function v, right? With parameters w, or the same thing that happens for the Q function, right? So today we're going to talk about neural networks as a way of coming with particular parameterization, right? And we've seen in some cases you can either take the state as an input and the output is going to be the value function, or you can take the state and the action as an input and the output is going to be the Q function for that state and action, right? So this is where, last class, I think we've looked at, if you want to build like a linear classifiers or mixture of linear classifiers, or if you want to build like a decision tree, you can do that. But today we're going to look at nonlinear functions like neural network functions. And for the rest of the course, all of nonlinear functions, neural nets, differentiable functions are going to be used to kind of have these parameterizations, okay? Right. And so today we're going to look at the differentiable function approximators. In particular, we're going to look at neural networks. Okay, so what is deep learning? You've seen this image, I guess, in many of you probably seen something like this. you have an input, which could be some high-dimensional image, or it could be some other high-dimensional sensory input, like a speech signal or a text or whatever that might be, and then you go through, multiple layers of representation, and as you're learning these multiple level representations, you can start picking up some interesting features. Okay, so today we're going to look at the definition of neural nets. We're going to look at very quickly how we can train them, right? Obviously, there's a lot of background material. If you've never seen backprop and stuff like that, there is a reading material for you to look at that, because I don't have time to go over it very carefully. But what I would like to do is I'd like to focus on more recent techniques like dropout, batch normalization, and unsupervised pre-training, so that you can use all of these techniques within reinforcement learning as well. Okay, when you're processing this, the high-dimensional input. Okay, so very quickly, what is an artificial neuron? You have a neural pre-activation, which just looks at the linear combination of your inputs. You have a neural activation function G. It's some nonlinearity that you're introducing, where W are going to be the parameters of the model, the weights, B is the bias term, and G is sometimes called the activation function. You can think of it as a nonlinearity that you're injecting into your model. Okay? In fact, if you look at this particular model in a single layer, and if you make your G be logistic, this looks like a logistic regression. Right? This is a logistic regression. So if we look at the activation function, the range is determined by your nonlinear function G, and the bias only changes the position of the riff, right? So the bias controls the position of, the hyperplane here. Some of the most commonly used activation functions, sigmoid activation function, which has this form of 1 over 1 plus e to the negative of the input. It's always positive, it's bounded, it's strictly increasing, right? These are probably the most commonly used nonlinear activation, sigmoids. Another very commonly used recently activation function is rectifying linear unit. It just has a simple form of taking the maximum of 0 or a, your total input, which basically says if your total input is negative, you set it to 0. If it's positive, it's just a linear function. So it's bounded below by 0, always non-negative, but it tends to produce units with sparse activities, right? Because in many cases, some of the units are going to be exactly 0. It's not upper bounded. In practice, people typically bound it so that it doesn't become too crazy, but the activation cells are not bounded, and it's strictly increasing. Okay? So this is probably the most commonly used nonlinearity. The reason why people typically use it is because it's not like this particular nonlinearity somehow is more expressive than the sigmoid. But I think that in many cases, these particular nonlinearities has two advantages. One is that activities are sparse, which is good. The second one is that you don't have to, computationally becomes much cheaper to compute. You don't have to, exponentiate things. Because exponentiating things is computationally intensive. Right? If I have to compute exps. Anytime you involve exps, it's computationally expensive. Now, there are ways of maybe making it more computationally, better. But at the same time, this is a very cheap operation to perform. Okay. So this is what the single hidden layer neural net would look like. You have inputs. You take the linear combination. You have a hidden layer activation. So this is h of x. And then you have an output layer activation. So you take the linear combination of these hidden units and you pass it through some activation function, output activation function. So output activation function will control what problem you're trying to solve. In the case of reinforcement learning, if you're deciding between 10 different actions to take or finite number of actions, then your output is going to be a softmax. Think of a classification system, right? Because you want to produce a distribution of a discrete set of actions. If you're working with a continuous control, where you're trying to predict, let's say, velocity or acceleration or a position, then this output function might be just the identity, right? Because this whole thing here is going to be real valued output. If it has to be positive, you can constrain it and maybe like a ReLU or something like that. So depending on what the problem you're trying to solve, you will be choosing different output activation functions. And then the extension of a multi-layer neural net is pretty straightforward, right? You basically, repeat the same procedure, the same thing multiple times. So you have a layer pre-activation for layer K, just taking a linear combination of the hidden units activations in the layer below. You pass it through nonlinearity, and you do it K times if you have K hidden layers. And then you have an output layer, right? Which again passes through some output activation function. Okay? Capacity of neural networks. So here's an intuition what these models are doing. Every single hidden unit, let's say it has this particular form, it's a threshold hidden unit, it kind of finds the separator, right? If the total input below the threshold, you set it to -1, or in this case, -1. If it's above the threshold, you set it to +1, right? So each unit here is a linear separator. But once you start combining these units together, you can actually get a very nonlinear decision boundary, right? As is shown over there. And so in principle, a single layer neural network can model fairly complex decision boundaries, right? So here's a setting where with enough nonlinear hidden units, you can construct a network that basically assigns this to class 2, this to class 2, but this region to class 1, this region to class 1, right? So the decision boundaries can be fairly complex, right? Think of, comparison to logistic regression or some linear separators. And that's why the power for these models is coming, because you can really reshape the inputs. You can really construct fairly sophisticated decision boundaries. There is a universal approximation theorem, which essentially is telling you that a single hidden layer neural network with a linear output unit can approximate any continuous function arbitrarily well, given enough hidden units, right? And that also applies to sigmoid or 10H or other nonlinearities. But this should come as no surprise, right? Because no matter what function you have, imagine that with enough hidden unit, each hidden unit just locally approximates the function. So if you stitch them all together, they can approximate any continuous function. Okay. However, this doesn't mean that there exists a learning algorithm that can find the necessary parameter values, right? So this piece doesn't exist. But at the same time, it does show that a single hidden layer neural networks are universal approximators. So which is nice. Now, how do we train these models? Very quickly, much like any other statistical machine learning model, we're going to be using empirical risk minimization, right? So we have to define a loss function. So let's look at the loss function. The loss function in supervised learning, in this case we're just looking at supervised learning, the loss function is a function of the output of a neural network. Let's say it's either a distribution of a class as a softmax output, or maybe it's just a real valued prediction. You have some labels y, and you have a loss function that's essentially looking at the mismatch between prediction and what the target is, right? Different loss functions will lead to different objectives. And then you also have a regularizer, right? So learning in this case can be cast as an optimization, right? So everything you're doing is just optimization. So for classification problem, we would like to minimize the classification error. But loss functions can sometimes be viewed as a surrogate for what we want to optimize. In many cases, if you try to optimize classification error, this objective function is non-differentiable, right? Think of like optimizing 0-1 loss. Like, how many examples did I get right? So in many cases, the loss function is going to be we're going to be using as a surrogate for what we want to optimize. Think of softmax or cross-entropy error function, which is just an approximation to the 0-1 loss, right? But it's differentiable. But in any case, if you think about how we set up the problem, it's no different from any other statistical machine learning technique, right? You have a loss function, you have a regularizer. So how do we train the model? Very simple. You initialize the parameters of all the layers. For each training example, this is stochastic gradient descent, you compute the gradient of the loss function with respect to the parameters of your model. You also need to compute the gradient of your regularizer, because your regularizer is a function of theta. And then you update your theta, right? You move it in a direction so as to minimize the loss. Okay? So this particular formulation shouldn't be as surprising. This is your standard stochastic gradient descent. Pick an example, you compute the gradient of your loss, you compute the gradient of your regularizer, you update the parameters, and you proceed. Okay? Obviously, you know, this is just standard SGD. There are a whole bunch of different, if you're interested in optimization, there's a whole bunch of different literature on how do we optimize, there's second order methods, and you know, a whole bunch of different things you can do to make optimization be better. Okay? So what do we need to do? To train the model, we need to define the loss function, right? So that's your choice as a modeler. You need a procedure to compute the gradients of your loss function, right? You also need to define a regularizer, and you need to define its gradients, right? So you need to be able to compute the gradients with respect to the regularizer. Okay? So a lot of work recently kind of focuses around, you know, how can we make sure that we can compute gradients efficiently, right? And there's a whole bunch of work on distributed computing. How do we scale it to large scale problems, parameter servers, and stuff like that. There is also some work on finding good regularization techniques, right? Are there sort of good regularizers, new regularizers that we can introduce to make sure that we have good generalization performance of our model? Okay. Now let's look at the way how we compute the gradients. The gradient computation is done through backpropagation algorithm. I hope that many of you have heard about backprop algorithm. Let's look at the computational flow chart of how we're going to be doing computation in these methods. So there's a forward propagation, which can be implemented as a cyclic flow graph, represented as a cyclic flow graph. And forward propagation typically can be implemented in a very modular way, right? So for each box can be an object with an approf method. So for example, given x and the parameters, we compute the pre-activation, right? We take the pre-activation, we pass it through nonlinearity, like ReLU or sigmoid, we get the hidden states, and then we repeat. Okay? So now you have a forward prop. Sometimes if you look at the software, like TensorFlow, PyTorch, or a whole bunch of different software, there is something that's called fprop, forward propagation method, right? And a lot of work is done on trying to optimize this computation, right? Because if this computation takes a long time, imagine you have a robot, you observe some image or some input, and you're trying to take your representation, pass it through the graph, let's say multi-layer network, in order to produce a distribution of possible actions. And then you pick the action to take, right? So this procedure needs to be fast. In fact, I always joke, there was 2 or 3 years ago, there was a company, Nirvana, that basically said, we're going to design a hardware piece so that we can speed this computation way faster than any of the existing algorithms or any of the existing hardware. You know, just basically speeding up linear combination, matrix, x times matrix multiplication, passing it through nonlinearity, right? Which seems like how much faster you can do it. But they've managed, you know, to build something that works really fast, right? And then they sold the company to Intel for $100 million, right? So that tells you something about, you know, how important this piece is. So if you can figure out how to do matrix vector multiplication and pass it through ReLU even more efficiently, you can make twice as much, right? Anyways, this is something, and then obviously when you're running these things on mobile devices or embedded devices and your robot and such, obviously this needs to be done very fast, right? You can't sort of like, here's your state, and then you're sitting around for a couple of minutes figuring out what your next action should be. The backpropagation method works in a backward way, basically. You compute the gradient of the loss with respect to each of these boxes in reverse order, right? So by calling backprop in reverse order, you're basically obtaining a backpropagation algorithm. Backpropagation algorithm, you think of it as nothing more than you have a loss function, right? And you have this differentiable mapping that maps x all the way down to the loss. And you're essentially using the chain rule, classical chain rule from calculus, to compute the derivatives with respect to all of the parameters in these boxes. That's all that is. It took people 30 years to figure out how to do that, which is surprising, because in the 50s, people came up with these models, in the late 50s and early 60s. And only in the 80s, there was an algorithm proposed by Rumelhart and Hinton and colleagues that basically showed that you can use chain rule to backpropagate the errors of your loss function through these multi-layer neural networks. And that basically gave rise to, training algorithm for these models. And even today, just doing gradient descent is one of, one of the gold standard algorithms, backpropagation. It's very hard to beat in practice with anything other than, obviously, you're doing gradient descent, it's very hard to beat it with other methods that don't use gradient descent. Now, model selection. How do you choose between different models? So you train your model on a training set, and then you use some validation set to choose hyperparameters. Think of choosing the number of hidden layers. Think about choosing the learning rates when you're doing optimization using gradient descent. Think about choosing the number of iterations that you're optimizing the system, right? Typically, you use it, you do it on the validation set, and then you estimate generalization performance on a test set. For many of you, this is basic, but make sure that you have a very good understanding of what's a training set, what's a validation set, and what's a test set. Because it happened before when, with a homework assignment, people report results on the validation set without touching the test set, or you do like your hyperparameter choice on the test set and you say my test results are better than the baselines. Well, of course they're better because you're tuning your algorithm to the test set, right? So, make sure that, when you do your homework, you very clearly separate your training set, which is what the optimization happens, your validation set, which is, not the same as a training set. You're doing some hyperparameter search on that. And then really, you're doing sort of a good job at evaluating your model on some held out set. And the idea is that you want to be able to look at the behavior of the model on unseen examples. Right? How well your model generalizes to new examples. One particular strategy, which works remarkably well, is early stopping. So the idea here is that if you're doing training of your model, right, as the training proceeds, given enough capacity of your model, your training error will be very close to zero, right? But at some point, the model will be overfitting. So if you're looking at your validation curve, this is the point where you'll start overfitting, right? So this is a choice where you're basically saying, well, I'm going to stop here, right? And that's a very good sort of practical regularization method. I think it was invented by computer scientists when we didn't have enough resources, compute resources. So you're training your model for 2 days, and then you basically say, I have to stop, right? And then you basically say, well, it's early stopping, right? It's good. So by lack of resources, you're discovering these good regularization techniques. But this is actually a pretty good one to use in practice, early stopping. A couple of things also I want to emphasize. In many cases, you're doing updates, parameter updates, based on mini batch of examples instead of a single example. So when we think about stochastic gradient descent, we typically think about pick an example and just update the parameters. Pick another example, update the parameters. In many cases, it's easier to deal with batch of examples, right? Where the gradient is the average regularized loss for that mini batch. So typically, mini batches would contain, 128, 256 examples. You can get a more accurate estimate of the gradient, but the most important thing is that you can leverage matrix operations. So for example, if you're using GPUs or modern hardware, whether you're processing one example or 100 examples, the speed is about the same, right? So if you take into account communication costs, it takes you to load on the GPU and do the processing, it turns out that the optimal kind of way is to actually operate on a batch of examples. So if you think about reinforcement learning, when we looked at, in our last class, when we looked at replay memory, what typically happens is that you have your set of a replay memory, and then you sub-selecting some examples at random, you're forming a mini batch, and you do the update on that, okay? As opposed to just doing update after every single example. There's nothing wrong with doing just updates after every single example, after every single experience that you're seeing, but just from like wall clock time, it's much better to be operating on mini batches. The other thing that you should also know about is the use of momentum. And if you look at the definition of the momentum, you're basically using the exponential average of previous gradients. So here's your gradient for a particular example, right, of your loss function, plus beta, some hyperparameter. And this is the exponential moving average of your previous gradients, right? So this can get you, it can help pass plateaus more quickly by gaining sort of momentum, right? The intuition you should have is that if at this particular example, your gradient points this way, you go to the next example, your gradient points this way. You go to the next example, your gradient points this way. Then the average of these gradients is basically pointing this way, right? So you don't get distracted by too much noise in the gradient, right? So you kind of like maintain the exponential moving average, and momentum turns out to be super important for optimization. If you're publishing a paper and proposing a new optimization technique, and you don't compare it to stochastic gradient descent with momentum, you're cheating. Because this thing works remarkably well for a lot of problems. It's very hard to beat in practice, basically. Okay, so, and then now what I'd like to do, any questions on this? So whenever you're implementing these techniques, obviously, whatever your loss function is, remember your loss function here could be TD error loss, right? It could be the Monte Carlo loss that we've defined. So once you have, let's say, TD error loss, then again, you can compute the gradients of this guy here. So all of these techniques of maintaining the momentum and the early stopping and such basically are still valid techniques, okay? Okay, so now what I'd like to do is I'd like to talk a little bit about some of the more recent techniques, because I think that these ones, many of you probably know about these, but it's important to know about these techniques because pretty much if you combine dropout with batch normalization with momentum, you pretty much get basically the current state of the art optimization for these models. It's very hard to beat the combination of these three. And that's the dominant technique that a lot of people are basically using today. Even though there's a lot of work on various variations and second order methods and so forth, these ones are basically the dominant ones. It's like, the trick is anytime you read a paper and somebody introduces the algorithm and lists a whole bunch of different algorithms, competing algorithms, as a practitioner, you always choose the second best, right? You don't get the joke? The second best is always the one to use, right? So if I develop a new algorithm and I say, look how much better compared to this technique, this other technique of batch normalization, dropout, and such, you know that the second one actually works. All right. So let me just get a little bit of intuition of what these models are doing. So deep learning is really the research on learning models with multi-layer representations, right? And again, with the connection of reinforcement learning, it's just a function approximation that we're using, right? You have a multi-layer feed-forward neural networks. You also have versions of multi-layer graphical models. So not necessarily deterministic functions like neural networks, but you can look at deep belief networks, deep Boltz machines, variational autoencoders. These are all instances of multi-layer graphical models with non-linearities in them, right? So when we talk about deep learning, it's not just optimization of neural networks. Each layer learns distributed representation, and that's very important. So units in a layer are not mutually exclusive. You can think of each unit as a separate feature of the input, right? Does this feature exist or not? If the unit is active, this feature exists. Two units can be active at the same time, right? That's important. That basically there's a notion of distributed representations. And then units do not correspond to partitioning of the data. So think clustering, right? In clustering, in input, any particular input can only belong to a single cluster, right? Here, that's not the case, right? Each input can activate multiple units or multiple features. So that's very different from kind of mixture-based models or partitioning-based models. Let me give you an intuition. So if you look at local versus distributed representations, and both have advantages and disadvantages, obviously, right? So for the local representation, if you think about clustering, if you think about nearest neighbors, if you think about radial basis function SVM, RBF SVMs, local density estimators, what essentially you're doing is you're partitioning your space, and you're essentially learning a prototype for that partition of the space, right? That's effectively what's happening. So parameters for each region of the space. So number of regions is linear with the number of parameters. Okay? Obviously, once you start getting into high-dimensional spaces, then these techniques become more and more problematic, right? Because you suffer from curse of dimensionality. Distributed representations, like if you think about PCA, for example, many of you probably know what principal component analysis is. Factor analysis, RBMs, Boltz machines, sparse coding, a whole bunch of different deep models. They sort of have this distributed representation, right? So think of it as follows. You have two units. You have some hidden latent or hidden variable that partitions the space, okay? And then you have another hidden unit that partitions the space. You have another hidden unit that partitions the space, right? So now each parameter affects many regions, not just local ones. So every time I introduce a new hidden unit, it affects many regions. The number of regions grows roughly exponentially in the number of parameters, right? So there is some advantage to these models as well. Okay, and that's important. I think that in many cases you see these distributed representations are actually far more powerful compared to local representations for most of the problems. Obviously, there are some settings where local representations are the way to go. And then there is also inspiration from visual cortex. Kind of inspiration from the human visual system, right? You have an image, it seems like the V1, the visual area 1 cortex of your brain basically detects some edges, and then there is some kind of local combination of edges that you're detecting, and then you're kind of recognizing a face, right? So if you're interested in connection between distributed representations and deep learning to neuroscience, there is a bunch of work in that space as well. Of course, we have no idea what's going in human brain. So every sort of connection we have so far is kind of, just an inspiration. So let me show you a couple of things. Why training these models is hard. And it's generally hard if we think about training within neural networks, standard neural networks. You can now guess that it's going to be even harder in the reinforcement learning objective, right? Because if your reward signal is sparse and training is hard, then you're kind of combining both of these problems together. So learning these things become even harder. So the first hypothesis that why the training is hard is basically underfitting, or the vanishing gradient problem, right? So generally, you can have these saturated units that basically block gradient propagation. And this is a very well-known problem in recurrent neural networks, right? And there's been some work that basically said, look, if I construct a model with 100 layers, you basically can't learn them, right? Like, obviously, you have more parameters, you have bigger capacity, so the model should be able to at least learn as good as a 20-layer neural network, right? But it turns out just optimization becomes hard and you can't really learn much. So there's been a few papers like residual networks or highway networks that basically introducing skip connections so that the gradient can propagate easier in these kind of very deep networks. So changing your architecture to trying to avoid this problem, right? So that's one hypothesis. On the other hand, the second hypothesis, well, the first hypothesis is underfitting, right? So basically a lot of work is happening in the space of, can we better optimize these models? Can we change the architecture so that we can optimize these models? So for example, you can use better optimization tools, like we're going to talk about batch normalization. We can try to look at second-order methods like K-FAC models that basically try to use the structure of a neural network to approximate the Hessian or the Fisher information matrix, which allows you to, again, perhaps do better optimization. So there's a lot of research in that space. And then obviously, there is even more work in the use of GPUs and use of distributed computing, right? If I have these large-scale problems and I really want to optimize them properly, then I'm going to be distributing, my gradients across thousands of machines or thousands of GPUs and try to do the optimization, right? This is actually where a lot of companies are focusing their efforts right now, right? Because if you have very large problem, large data set, you want to be able to train these models. Optimization is an issue, so you do distributed training. The second hypothesis is overfitting. So the hypothesis is kind of like counterintuitive to underfitting, right? The hypothesis is the following. What people have noticed in practice is that when you're training these models, these deep models, you want to start with a model that overfits. You want to start with a model in such a way that if you fit your data, you get zero training error. Okay? So in many cases, you can design a model that basically, think of an ImageNet dataset. It's a very large-scale visual dataset, 1.2 million images. Most of the algorithms or most of the architectures, if you don't regularize them, will achieve zero training error. And that's important because it basically says that at least I have enough capacity to learn or memorize my training data, right? And then what I'm going to do is I'm going to try to use better regularization techniques. Regularization techniques such as unsupervised pre-training or stochastic dropout. Okay? Does that make sense? In fact, if you're playing with these models, given a particular data set, the first thing for you to do would be to train, give enough a capacity of the model, a large model, train a larger model, forget about regularization, just make sure that you get zero training error. Because that way you can test your optimization and you can test, that you have enough capacity in your model to actually reach the training error. If you're also interested in that particular space, there is some work where people are trying to look at topological structure of your data set to try to figure out what kind of a capacity network you need in order to be able to fit or overfit to that particular data set. Okay? And then for many large-scale problems, you'll need to use both. You want to have better optimization techniques. At the same time, you want to have much better regularization techniques, right? So the two problems are kind of, very much intertwined together. So let's look at the unsupervised pre-training. So unsupervised pre-training is popular, particularly in the settings where you don't have enough labeled examples. So think about the setting where you have lots of unlabeled data, but you only have limited amount of labeled examples. Then these techniques, these unsupervised pre-training techniques, can dramatically help get better generalization. And the idea is the following. You want to force the network to learn some structure, latent structure of input distribution. Okay? So the question is, why is one a character and the other one is not? Right? Obviously, the input data has some structure in it. It's not just a random permutation of pixels. Right? And so what you'd like to do is you'd like to get your network parameters or hidden units to encourage the units to encode that particular structure. Right? So you basically want to say, I want to build my deep network, but I also want to have a bias that whatever representations I'm learning are also going to be useful for reconstructing the original input, okay? Or generating the original input, which means that it knows something about the shape of this data, right? Now, there is one caveat, which is, if you're trying to solve the problem, which is the following, you take this pixel number 1. If it's black, it's class 1. If it's white, it's class 2. And that's all you're interested in. Whatever happens in this image is irrelevant. Then unsupervised pre-training will not work. In fact, it might work worse than supervised learning, right? Because if you believe that your label that you're trying to predict or the action that you're trying to take has nothing to do with the original input, and is only a function of one particular feature, and everything else is just a distraction, then unsupervised pre-training will not help, because unsupervised pre-training will try to say, encode this particular structure in the input. These unsupervised methods are also now becoming popular in the reinforcement learning domain, right? The reason why, because in the reinforcement learning domain, your rewards are very sparse, right? So now there's been a few papers where you're kind of saying, well, can I at least do some learning of my model, of my architecture that can encode something about the environment, right? Maybe something about the physics of the environment. Like laptops don't float in the air, right? They're typically on the floor. Or, when I take a particular action, I know what the future might look like, right? Conditional on the action, I know what the next state might look like. And this is, again, comes to this particular problem, trying to model the distribution of the next state given the current state and the action, right? And this is harder task than supervised learning, right? Because you want to encode this particular structure, and so we expect less overfitting. And that's the idea. So how do we do that? One particular way of doing it, very common way of doing it, is to use feed-forward neural networks to basically reproduce its input at the output layer. So these are known as autoencoders, right? You have some input, you go to some hidden state, and then you reconstruct yourself. So think of it as a compression technique. It traditionally was viewed as a compression mechanism, right? So how do I compress my input in such a way that I can almost perfectly reconstruct it? Now, there is one caveat here. Let me look at the equation. So the equation kind of looks like take the weighted combination of the inputs, pass it through nonlinearity, and the decoder basically says take these hidden activations and basically reconstruct back the original input. So in this case, if the input is binary, you can use sigmoid nonlinearity, right? And then you can basically, this is for binary units, and then if your loss function for binary units, you can construct, the cross entropy loss. Okay. Let me just go back here. So that's what you can do. Now, what's the caveat here? in the traditional autoencoders, your hidden state space or your hidden space, the dimensionality of the hidden space should be smaller than the dimensionality of the input space, right? Because otherwise, if I just make this be identity and I make this be identity, then I have a perfect autoencoder, right? I have zero training error and I have zero test error because I'm not doing anything to my data. I'm just keeping it. And so there's been a lot of work on trying to figure out, if you're compressing it, then you can think of it as a dimensionality reduction. Right? You have high dimensional data, you're compressing it. If you want to find some other features like, what sparse coding does or various other versions, then you have to introduce additional constraints. Like, for example, sparsity is one very useful constraint where you're saying, this could be very large, but only a few units should be active. Everything else should be inactive. And that tends to learn very good features of the input. So for the binary units, you can use cross entropy. For the real valued units, you can use basically the squared loss. Right? It's just the sum of the squared differences, and then you can use the linear activation function at the output. Okay? So these are very basic kind of unsupervised building blocks. And there's a whole bunch of literature if you're interested in how to make these things more robust. There is like convolutional encoder decoder. There's a whole bunch of different kind of methods that extend this basic idea. So now if you can use pre-training, you can use a greedy layer-wise procedure. You train one layer at a time with unsupervised criteria, right? The key idea here is you're using unsupervised learning. You don't touch the labels, right? So think in reinforcement learning, I give you the state, and maybe you're trying to predict the next state, condition on the action. You don't need the reward function for that, right? So you can train one layer at a time. You fix the parameters of the previous hidden layer, and then previous hidden layers can be used as a feature extractor. So for example, let's say you train this autoencoder. You go up, you go down, right? And then once you finish training, you can take the hidden features and basically say, these are my features that I'm extracting from my data. And then you train the next layer autoencoder, and then you train the next layer autoencoder. Right? So that's a very cheap, not cheap, but it's a very kind of intuitive procedure. You just try to do compression. And exactly how you formulate this problem, are you finding sparse features? Are you using denoising autoencoders? Are you using sparse coding models? There is a whole bunch of different papers pretty much doing all kinds of variants for these training. Right? And once you do that, once you kind of like pre-train all of these layers, and notice what happens in this case. These hidden features are good at reconstructing the data. So it'll capture something about images or something about your data. These features are good at reconstructing this data. Right? So it'll start capturing something about these high-level features. These features are good at reconstructing this data. So it'll capture something about, these features. So if you go in this model all the way up and then all the way down, you will end up having a pretty decent reconstruction of the data. So it's kind of just learning something about reconstructing the data, right? And that's the bias that you put into your model, right? And now you basically unroll the whole model. You call the last phase the fine-tuning phase, which is basically you fine-tune all of the parameters to the supervised task that you might have at hand. And these representations are going to be adjusted to be more discriminative or to try to, optimize for a particular task that you're trying to optimize. Okay? And again, the bias, or at least the inductive bias that you're placing into these models is that whatever the pre-training algorithm does in terms of finding these weights such that you reconstruct the data, the inductive bias is that those representations are also going to be useful for classification or for taking the action in your reinforcement learning application, right? If your reinforcement learning application, if taking an action has nothing to do with what the world looks like, then this method will fail, right? So you have to always be, kind of have some notion of understanding, does the understanding around the world helps me in my reinforcement learning application? Maybe it doesn't. Maybe all I need to do is I need to detect like one little spot over there, and it doesn't matter what the rest of the scene looks like. And depending on this one particular spot, I know what the right action. In this case, this unsupervised pre-training will not help you much, right? This also kind of like is this unsupervised learning is also motivated by the way that kids learn, right? The way that kids learn and the way they operate is that you're not really providing any labeled examples or any rewards frequently, right? The kid kind of goes around, looks at stuff, builds some kind of internal representation of what the world looks like, and then once in a while you take an action, you get big negative reward. You start realizing what's going on, right? So you take a big positive reward and you adjust appropriately. So there is sort of a motivation for doing this unsupervised learning. Okay. And the other thing I want to talk about stochastic dropout technique. It's another technique which is kind of pretty much you have to use it if you want to build state-of-the-art algorithm in terms of classification accuracy and such. So let's look at what the dropout does. It's actually pretty simple algorithm. The key idea is what you want to cripple a neural network by removing hidden units stochastically, right? So here's an example. Each hidden unit is set to 0 with probability 0.5. Okay, so imagine that you pass your data through your neural network, and for every single hidden unit, for every single example, you flip a coin, and you basically say set it to 0, right? And hidden units, what happens in this case is that hidden units cannot co-adapt with other units, right? So that's why they have to be generally more useful. So what that means, co-adaptation basically means that it's not like this, if this hidden unit takes a value and this hidden unit takes another value, and they're correlated, highly correlated, right? Then they can co-adapt. They can say, oh, if I see this feature and this feature, that means that's a 2. Right? Because at any point in time, you can drop one of them, right? And you still need to be making good prediction. Think about, for your final project, you're going to be working, let's say, in the groups of 3, right? Imagine you show up together, and every single person drops out of the meeting with probability 0.5, right? Now, if you can succeed in your project, nonetheless, that's good. You have a very robust system. If only one guy on your team is doing all the work, right, and the other 2 people basically just relax, then obviously that's not going to be good, right? Because at any point in time, the person who's doing all the work drops out, and then you basically have nothing, right? So what this technique forces you to do, it forces these units, each unit, to be generally more useful. It's almost like a perturbation of the system. You perturb your system and say, on the perturbation, I need to make sure that you still correctly, predict the class. So one thing that I also want to point out is that generally, the probability of 0.5 works pretty well, right? But it doesn't have to be 0.5, right? It generally can be anything anything other than that. It's just that when you write a paper, it's much easier to say, I use dropout with probability 0.5 because nobody's going to be questioning you. If you got to choose a number between 0 and 1, what is it that you would choose? 0.5, right? If you're writing a paper and you're saying, I'm going to be using dropout rate of 0.3567, right? Then obviously, if you think about minimum description length, right? Obviously, reviewers will be asking a lot of questions because that would somehow mean that using a dropout rate of 0.3569 might not give you the same results, right? But generally, 0.5 works fairly well. Sometimes people do hyperparameter search. Sometimes you can choose 0.2 or 0.4, but generally 0.5 works reasonably well. So how do you actually implement this? The beauty of the algorithm is that it's cheap to implement. It's actually just one line in your code, right? And what is this one line? So this is the algorithm for a forward propagation, right? You do the activation, you compute your hidden units, you look at the output. And all you're doing is you're multiplying it by the mask, right? 0, 1 mask. The only important thing I want to emphasize here is that for the same example, the choice of which units you drop out will be different. Every time you see an example, you choose what units to drop. It's not like for this example, you drop these units. For this other example, you drop these other units. No, you always make stochastic choice. So even if you see the same example multiple times, you'll be using different networks, or different hidden units. Okay? So it's cheap to implement because you just create this mask, you do element-wise multiplication, and then that's it. One line in your code. How do you use, let me just see if I, hold on. One other thing I also want to emphasize, if you're looking at the backpropagation algorithm, the backpropagation algorithm remains the same. In fact, you don't need to change anything. Right? The reason why you don't need to change anything is because units that you've dropped out will have value 0. So when you do backpropagation, you're going to be multiplying, the outgoing weights with the h, and units that are dropped out will have value 0. Right? So it's kind of nice because the algorithm, the really one line you need to change in your code is this multiplication. Nothing else changes. Right? So that's why I think a lot of people are using this algorithm, because a single line in your code and you don't even need to change the gradient calculation. Everything remains the same. So I think that's important. How do you use dropout at test time? Well, at test time, you're basically replacing masks by their expectation. And this is simply the constant vector of 0.5 if the dropout probability is 0.5. Okay? So this is just basically saying that, if you have a hidden layer of size 100 and you use a dropout probability of 0.5, on average, only 50 units will survive, right? Plus minus some variance. So what happens at test time, you basically say, I want to use all my hidden units. I don't want to introduce any stochasticity at the test time. So I'm going to use all of my hidden units, but I'm going to scale the outgoing weights by 1/2. Okay? So that the total contribution to the layer above is still going to be on average 50. So really, you can write this down as a way of replacing the masks that you're multiplying, the stochastic masks, by their expectation. Yes?
So for this dropout usage at test time, it's basically scaling down the activations, right?
Sure, yep.
But I saw that in some deep learning frameworks like PyTorch, their implementation of the dropout is scaling up the activations at training time and do nothing at test time. Are these two equivalent, or?
I don't know. I don't think they're equivalent, but you could do that. Maybe in some cases that would work better. You do the dropout and then you're kind of like scaling things up. So you're maintaining it roughly the same. These are details. I don't think they're the same, but obviously how you do it at the test time or how do you set it up during training time is your choice. Right? Basically what you have to make sure is you have to make sure that the scaling is the correct scaling. Because if on average you're sort of activating only 50 units out of 100, and then at test time you're activating 100 units, then that's not right? Because that will overlap or oversaturate your network, and obviously. So you have to maintain the right scaling. And it turns out that for a single hidden layer, it's equivalent to taking the geometric average of all neural networks with all possible binary masks. So there is some interpretation of it that basically saying, look, if I let's say if I have 100 units here, then there are 2 to the 100 possible networks, right? In principle, there are 2 to the 100 possible networks. And what effectively I'm doing is I'm training all of these 2 to the 100 possible networks, but all of them share the parameters, right? And at test time, what I'm doing approximately is I'm taking geometric average of all of these networks. So that's one view of these models. Now, this is not quite right, because if you look at the multi-layer networks, the expectation of the sigmoid is not the same as the sigmoid of expectation. So you can't quite make the same argument, but at the same time, approximately, you could argue that that's what's going on. There is also nice work following up. There's been a lot of work that basically says, well, dropout can also characterize uncertainty. So if I actually have some time at the test time, I can run my model for the same example and I can do dropout multiple times. So every time I'm choosing a different network. And if I look at my output and uncertainty in my output, just the variance of the output, that can tell me something about uncertainty, right? So you activate 10 different networks, you look at the mean, you look at the variance, and the variance tells you something about how uncertain you are about this input, which is kind of nice as well, if you have compute time to do that. It also can be combined with unsupervised pre-training, and it basically beats regular backpropagation on many data sets, right? And it can also be viewed as an ensemble method. Okay, now for the last part, I'd like to talk about batch normalization, which is another recently introduced technique which works remarkably well. So let's see what this technique is. It has a very intuitive kind of appeal to it, you know, what's going on. And there's been a few papers, theoretical papers, trying to justify what exactly it's doing, but it's still kind of not very well justified technique at this point. So people have noticed in '98, Jan LeCun, that normalizing the inputs will speed up training. Okay? And that should come as no surprise to you, right? Imagine you have two features. The range of one feature is from -1,000 to 1,000. The range of another feature from -1 to 1. Okay? Now, if you initialize your neural network and basically say, I'm going to initialize my random weights to be around 0, and you start training the model, obviously one input will kind of drive your network, right? You kind of have this very bad parameterization. So normalizing the input can really speed up optimization, right? It's not like one network is somehow more expressive than another one. It's just being able to, you know, initialize your model in such a way that the optimization, it's easy to do optimization, right? So changing a little bit the landscape, the optimization landscape. The question is, could normalization be used at the level of hidden units, at the level of hidden layers? And this is what the batch normalization, which was introduced in 2014, is an attempt to do that. So batch normalization does the following. Each unit pre-activation, before it goes through nonlinearity, is normalized. And it's, you do the mean subtraction and you divide by standard deviation. Okay? And during the training, mean and standard deviation is computed for each mini batch. So imagine that you have a mini batch of 100 examples, right? You look at the hidden unit, you look at the total input to the hidden unit for those 100 cases, right? So now you have 100 numbers, right? You compute your mean, you compute the standard deviation, you subtract the mean, you divide by standard deviation, right? Now what's going to happen? What's going to happen is that you're basically saying the total input to each unit is going to always be 0 mean, variance 1. Right? So you're not going to have these weird inputs coming in. The input to the hidden unit is always going to be normalized. Okay? And the backpropagation will take into account this normalization, because the normalization itself depends on the hidden activations in the layer below. And the variance itself also depends on the hidden activations in the layer below. So you can think of it as like introducing an additional layer that computes the mean and standard deviation, and you're doing this correction, and then you go to the next layer. And you can backpropagate through that operation of computing the mean and standard deviation. At the test time, again, one of the things you want to do at the test time, you don't want to have any stochasticity at the test time. Right? You don't want to publish the paper that basically says, oh, with this random seed, my stochastic model actually does much better than your model, right? So generally, you don't want to have stochasticity at the test time. So what you do at the test time, you basically compute the global mean and standard deviation. So you run all of the examples through the network. You compute the mean and standard deviation for each hidden unit. You normalize it, and that's how you use it. Okay? So let's look at precise equations, what the model is doing. So let's say you have some values of x over some mini batch b. Notice x doesn't have to be the input. It could be the activation of layer 3, right? And so what you do, you compute the average of layer 3 hidden unit. You compute its standard deviation for that particular mini batch. You do this operation, you subtract the mean, divide by standard deviation. This parameter here is also plays a role. It's an epsilon that you sort of choose. So it's to make sure that you somehow don't get overflow, underflow stuff. Right? Sometimes you don't want to divide by 0 or some small number. And then you basically say, now my post-processing of this particular hidden unit is going to be, I'm going to take the normalized one, multiply by gamma, and add beta. So you're introducing 2 extra parameters for every single hidden unit. Okay? And the idea is that you're initializing it to 1 and you're initializing this to 0. But the idea behind this particular parameterization is that, in principle, you could undo the normalization. If I set my beta to be the mu sub b and I set my gamma to be the variance, then if I multiply it and I add, then I have the exact same thing as whatever the input is. And the reason why they've done it is they basically said, look, we're introducing 2 more parameters per hidden unit. It's not that much. But we can actually undo the normalization. So the network has the capacity to undo it. So in terms of the capacity of modeling, we haven't really reduced the capacity of our network. So it can still do whatever it needs to do. Okay? Yes, question?
Is there a reason not to use the global mean at training time?
The reason why is computing it becomes expensive. Right? Because the mean will change. So think about the hidden unit at layer 3. Depending on the parameters below, the mean of this thing will be changing all the time. And if you want to...
Just for the training input, though, it wouldn't make a difference?
What do you mean for the training?
Well, if you run through the training input and that doesn't change every epoch, right? And so you could use for the global mean for that, but where you're saying, at least for hidden layers, it is important to use the mean?
Yes.
Okay.
Because if, for the input, you can always compute the mean and standard deviation for the input, because the input doesn't change. But the layer 1 features will be changing. And so the mean and the standard deviation will be changing as the training proceeds. Right? And if you have a large data set, it's expensive for you to keep running a large data set to just compute the mean. So that's why a version of it is always to compute the mean and standard deviation on a mini batch. Right? It also has the advantage because if you happen to choose a mini batch that has some weird statistics to it, you're normalizing this particular mini batch. Right? So at any mini batch that you're working with, the network is always normalized. And that has an advantage. It's almost like you're doing data-dependent regularization. Depending on what data you see, you regularize it in a certain way, which is kind of unusual concept. But nonetheless, this is something that works surprisingly well. Right? There's some work that basically shows that what's happening here has some approximation to approximating the diagonal elements of the fish information matrix. You think of it as an approximation to the second order methods. Right? By doing this normalization, you're somehow reshaping the landscape, the optimization landscape, and so it's easy to optimize through. And there's been a lot of work. People are trying to use the same thing for recurrent networks, for convolutional networks, all kinds of things. And people are doing all kinds of normalization, trying to figure out, is there any way to kind of normalize things appropriately? In the space of RNNs, recurrent neural networks, that particular normalization doesn't quite work as well. And so people are doing layer-wise normalization, within layer, between the layers, and so forth. Right? So in some cases, it can help. And this is a linear transformation. So why do we normalize the pre-activation? Again, it can help keep pre-activation in a non-saturating regime, right? So it really is saying that whatever goes into the hidden unit before nonlinearity, before I apply nonlinearity, is always going to be normalized. So I never end up having these saturated units, which makes typically problematic because if your units are saturated, it's very hard to pass the gradients through them, right? So for example, think of a sigmoid unit. If the sigmoid unit is close to 0, 1, the derivative of the sigmoid unit is sigmoid times 1 minus sigmoid, right? So if the sigmoid is 1, then the derivative is 0. If the sigmoid is 0, derivative is 0. So you can basically see that if, once you start hitting these saturating regimes, your gradient basically shuts down. So you don't do any learning in the layers below. So this controls for that. And then you can also use the global mean and standard deviation at test time, right? So it removes the stochasticity. It requires a final pass where for the first and the last hidden layers, from the first to the last hidden layers, you propagate all training data, you compute and store the global mean and standard deviation, and then basically you use that. Sometimes you can also use exponential, a running average of your mean and standard deviation. So kind of like what we've seen at the momentum. So you can do that as well. Okay, so this will conclude us some of these techniques, and you will be using some of those techniques for your second assignment, if you want to. Next class, we're going to look at convolutional networks, more just for you to know what these things are. Because for your final project, many of you are probably going to be working with some simulators, and one way or another, you're going to be using convolutional neural networks.